Okay, welcome to the next video. This is Math 126. We're looking at section 4.3 and 4.4. So 4.3, we'll start there, is on log functions. So let's begin there. No, if I recall, there were no questions asked about 4.3, or maybe there was. I wrote a few down here. It looks like 22. Somebody asked about 22. But before we get there, let's do number 4. Take a look at number 4. Number 4 says to rewrite x to the y equals z. The exponent function that we have here, rewrite it as a logarithmic function. So we do that simply by noting that x is the base of the exponential, and it's going to be the base of the logarithm. And the base is written as a subscript down below everything else. And then the y and z kind of switch places over that equal sign, so it becomes log base x of z equals y. And so these two are equivalent statements. It's important to note that that's how you go back and forth between an exponential function and a logarithmic function. Right? And in fact, that's the answer to number 4. Let's look at number 10 as well. Number 10 says to go the other way, to write log. Oh, just kidding, it's a true or false question. And it says log base 4 of 1 over 16 is equal to 2. True or false. And it's easiest to rewrite this as an exponential in order to determine whether this is true or not. So to do that, I'm going to take 4, the base of the log, is now the base of my exponential. And again, these two switch, so it's 4 raised to the second power equals 1 over 16, which is clearly false. 4 to the second power is 16, not 1 over 16. So this is false. The answer to number 10 is false. Okay, let's look at 14. I did one of these. There's 3, I think. I did the last one. C. We'll call it C. It's not numbered or lettered in the homework, but it's the last one. So I did the very last one, which says evaluate. And I'm evaluating the log base 4 of 64. So it's just an expression right now. It equals something, and I don't know what that is right now, so I'm just going to say this is equal to, I don't know, and I just have to figure out what that x is. But in writing it as an equation, I can change it now and write it as an exponential. 4 to the x is equal to 64. And I know that 64 is 4 to the third power. So that is to say I have 4 raised to the x is 4 to the third. The only way this is ever going to be true is if x is 3. I can't have x be anything else other than 3 for this to be true, and so it must be x is equal to 3. And we're done. And let's look at 22. That was the one that somebody asked. And I think, if I remember right, they wrote down the answer and then asked, is this correct? So let's take a look at it. And I think they were right. It was log base x of 3 equals 1 over 3? 1/3? So we're solving for x. That means I can probably rewrite this as an exponential. X to the 1/3 equals 3. And I can solve for x by taking both of these guys and raising them to the third power. X to the 1/3 to the third is x to the 1/3 times 3, or x to the 1. And then I have 3 to the third is 27. And so x is indeed 27. So that's 4.3. Hopefully there's nothing too challenging. Again, if you find something you can't figure out, throw it in the discussion boards. We'll talk about it. Somebody will talk about it. I'm still going through those and answering questions that don't get covered, so throw them up there in the discussion boards. But let's move on here. Let's go to 4.4. And I think nobody asked questions about 4.4, so I'm just going to do a couple of things. 4.4 is on the laws of logarithms. And so let's take a look at one law here that says that if I have the log base a of something added to the log with the same base, it has to be the same base or this doesn't work, but if something else could be the same thing or something else inside the log. But if I have the sum of two logs with the same base, I can call that the log, a single log, with that base of the product of those two things inside the log. And so the log base a of x plus the log base a of y is equal to the log base a of x times y. Now you'll use that to solve number 2. Number 2 says take the log of 400. There's not a base written here, so we should know that that's a base 10 if it's not written. Plus the log of 25, and we're supposed to evaluate this. So the log base 10 of 400, I don't know what that is. If you throw it into a calculator, it's going to be a pretty horrific number, a decimal that goes on forever and ever. Log of 25, same story. They're not going to be pleasant numbers. But I can use this property up here to say that this is the same thing as having the log of 400 multiplied by 25. That, of course, is 1,000. $10,000, sorry. Nope, it's just 1,000. No, it's not, it's 10,000. Son of a... Okay. Alright. So then I've got this, and again, if I've got no base down here, it's a 10, right? So this is equal to, I don't know, it's still going to be equal to something, I don't know what it is, let's call it x. And therefore I can say, if I rewrite this in an exponential, it becomes 10 raised to the x is equal to my 10,000. But 10,000 is 10 to the 4th. And therefore x is 4. And I'm done. All right. Let's look at another log rule here. This is the difference. It's similar to the one we just did, but it's the difference of two logs. Again, I have to have the same base, so the log base a of one thing minus the log base a of something else is going to be the log, same base, but it's whatever's positive ends up in the numerator, and whatever is negative ends up in the denominator. So I have the log base a of x over y. And we're going to use that on number 3. Number 3 says evaluate the log base 2 of 10 minus log base 2 of 35. And then plus log base 2 of 112. And again, any one of these by themselves is going to give you an irrational number. And so it's best to just use the previous law that we did plus this one. And it's essentially, if I have log base 2 of 10, I can ignore this middle one for a second. Log base 2 of 10 plus log base 2 of 112 is going to be the log base 2 of 10 times 112. And then I have minus log base 2 of 35, so it's going to go in the denominator. So I'm using both of them kind of simultaneously. This is going to end up being the log base 2 of whatever's positive, whatever log is positive. The inside goes in the numerator. And the negative log, its innards go in the denominator, right? So I get the log base 2 of the fraction 10 times 112 over 35. Right? This all simplifies because 10 and 35, both divisible by 5. That leaves me with a 2 and a 7. 112 is divisible by 7. That is 16. And so in fact I get the log base 2 of 2 times 16, so I get the log base 2 of 32. And I'm supposed to evaluate that, so that equals something. I don't know what it is yet, but if I say it's equal to x, I can rewrite this as 2 raised to the x equals 32. And I know that 32 is 2 to the 5th. And therefore x equals 5. Okay. Alright, let's take a look at one more rule in this section, and then one more problem. This rule is very important. You'll see it come back in calculus and beyond. But it's the power rule. So it goes like this. The log base whatever of x, it doesn't matter what the base is. But if whatever's inside your log has a power, right, then you can pull that power out in front as a multiplier. And so it's that power then multiplied by the log base a of x. It's very useful because if I have something with a power, it comes out, it's no longer in a power, it's not an exponential anymore. So it's a nice way of getting rid of an exponential inside a logarithm. So let's take a look at number 9 and how we can use that here. This says to, I think 9 says break it up into different logarithms and then use all exponents, pull them out as coefficients in the front using this. So we start off with natural log of the square root, the fifth root of 2x squared y to the third. And you look at this and you say, how in the world is that supposed to help? But this fifth root can also be written as a fifth power. So I can write this as the natural log of 2x squared y to the third to the 1/5 power. And now I can use this rule to take the r in front. R in this case is 1/5. So I'm going to write this as 1/5 multiplied by the natural log of 2x squared y to the third. And I freed the whole natural log of that fifth root by simply pulling it out as a 1/5 multiplier. Now I want you to continue to break this up, so I'm going to use the sum formula. I'm going to go kind of backwards. The natural log of a bunch of junk multiplied can be rewritten as the natural log separate of each of these added, right? So be careful because I've got this 1/5 multiplied by this natural log. So if this natural log expands into a sum, it's still 1/5 multiplied by that result. So I'm going to write 1/5 multiplied by, and I'm going to open up a parentheses and then expand natural log. This would end up being the natural log of 2 plus the natural log of x squared plus the natural log of y to the third. And of course that 1/5 multiplied on all of them, so it would essentially distribute through. So I'll do that. I'll take the 1/5 and distribute it through. So that's 1/5 multiplied by the natural log of 2 plus 1/5 times the natural log of x squared plus 1/5 times the natural log of y to the third. Now the last thing that I have to do is make sure that all exponents come out as powers. So x has an exponent that needs to come out, y has an exponent that needs to come out. The 2 is fine, so this is then 1/5 times the natural log of 2. That's okay. The 2 just comes out as a multiplier, so I multiply 1/5 by 2, so that's just 2/5. So that's plus 2/5 times the natural log of x. And the same thing with my 3 on the y, comes out as a multiplier, times the 1/5 is 3/5, the natural log of y. And that is, I think, the solution that's in there, and that would be the correct one. So I hope that's helpful. That covers the general, the overview of the entire homework. So again, if you have stuff that doesn't get answered, throw it in the discussions, and I will see you next week.